Well, this is you might say, a slight departure from the usual. And I'm sure if you look at the title, you're going to say, well, how on earth does water play a role in the flight of birds and insects? And I'd like to try to convince you that there is an indirect effect. And I'm going to be describing this effect, and I'm going to be talking about the mechanism of bird flight. This is a speculative kind of presentation. And I'd like to suggest some mechanism that's different from a mechanism that you've been thinking of. So we look at birds, they're beautiful. The question about the birds is not why they look so colored and beautiful, but the question is, how do they fly? And it's not just a question of flying of birds, but also the flying of insects. One famous researcher many years ago said that the flying of bees is impossible, because if you look at the fragility of the wings and the weight of the wings relative to the weight of the insect, he said it's akin to a tissue paper lifting a tank. So anyway, so if you ask a child, or if the child asks you, how do birds fly? How do you respond to this? Well, most people would respond by saying, well, of course, the birds fly by flapping their wings. And that's an easy response, but one of the problems with that is that sometimes birds don't flap their wings. Outside my home in Seattle, on the top of a tall tree is, in fact, a nest of eagles. And the eagles will leave their nest. They may occasionally flap the wing, but they don't flap their wings. And they leave their nest, and they can go against the wind, with the wind, 90 degrees to the wind. They can glide up. They can glide in a straight path or sometimes down. And the question is, well, how do they do that? And it's the same with some other birds. Albatrosses, for example. Albatrosses can glide over waters sometimes for days without settling down. And mostly they do this by having their wings out like this without flapping. So the question is, well, how do they do that? This is an integral part of flying, and what's responsible? And so the question coming from someone who has been studying water is, well, is it possible that water plays some role in this process? A similar problem exists with clouds, and clouds are, of course, mostly water. And the question is, what keeps the clouds aloft? So, the clouds basically consist of little droplets that somehow are held together to form the condensed cloud. And if you estimate the weight of a cloud, someone has done this, and you can do it in terms of kilograms, or you can do it in terms of elephants. And elephants are kind of easier to imagine. A cloud like this may consist of the weight of several thousand elephants. And so, given the weight, the question is, well, how come the cloud doesn't come down and hit you on the head? Well, sometimes it does rain, but most often the clouds are up here. And so what keeps the clouds aloft? Perhaps this is a question that you haven't thought about, what's going on. You see it every day. And so I would like to raise the question, is it possible that this could have something to do with electrical charge that keeps it? Sorry, there's a question back there? Oh, no slide. Oh, okay. Is there something I should be doing, or? Yeah, most of us, we look up in the sky and we don't even think about, oh yeah, there are the clouds. And how come sometimes it rains and sometimes it doesn't rain? These are questions that should be foremost in our minds, but we don't think about them. Okay, now, why do I suggest that maybe charge is involved? And it has to do with the Earth. So this is something that many of us don't don't know about, but others do. So the Earth, in fact, has a net negative charge, and the atmosphere is positive, and so there's an electric field, not a magnetic field that runs this way, but an electric field that runs at right angles to the surface of the Earth. And I studied electrical engineering in my undergraduate days, and if someone had told me that the Earth is not absolutely neutral, I would have said, you're nuts, crazy. But I had a Russian guy in my laboratory, Andrei Klimov, who's a very creative guy, and as he was departing in his last days for Russia to return home, he started talking to me about the Earth's electric field. And I said, Andrei, you're crazy. You must have too much vodka or something. And Andrei said, well, you're crazy because everybody in Russia knows about the Earth's electric field and that the Earth is negatively charged. And, I actually had trouble believing what he was saying because how could it be? How come I had never heard of this, and nor had any of my friends or colleagues? And next morning, one of my students walks in with the classical lectures of Richard Feynman, and there it was, Volume 2, Chapter 9, about the Earth's electric field and the negatively charged Earth. And you could have knocked me over with a feather. And in it, he was talking about the origin of the electric field, and he mentions also that the magnitude of the Earth's electric field at the Earth's surface, like right around here, is about 100 volts per meter, and that's a pretty big electric field. And he mentions that for someone of my height, it means that my nose is 200 volts positive compared with my toes, and that impressed me. So the major point is that the evidence for the Earth's negative charge is abundant and clear, although those of us who come from the U.S. have never heard of it. I'm not sure that all Russians know about it. I think Vladimir could inform me about that, but yes. You know. Okay, you guys know. I guess it depends on your political outlook. Okay, so how come? Where does it come from? Well, in Feynman's book, remember he gave his lectures in the 1950s, and it was a time ago, but the suggestion or the idea where it might come from has to do with lightning. So in some regions, lightning occurs every day in the afternoon, and the idea is that the flashes of lightning bring negative charge to the Earth, and the Earth can't get rid of these negative charges fast enough, and therefore the Earth retains a negative charge. And that's possible. Another idea has to do with the water in the Earth. As you well know, the Earth contains lots of water. And I'd like to mention to you about the EZ water. I know that some of you know. This is described in my recent book. And I think a possible culprit is EZ water. And why do I think so? Well, EZ water forms in the waters of the Earth in many different places. One is that it forms with negative charge. It forms next to various hydrophilic surfaces, and even, it appears, around ions as the hydration shell around it. It occurs at the air-water interface. It builds there. And on the Earth itself, in plants and such, it fills the cells of plants. And we found it has a negative charge. And the complementary positive charge is sitting in the water beyond. And so what happens is that as the water evaporates, some of the EZ evaporates in large clusters, as we showed experimentally. But also the protons or hydronium ions evaporate as well. But much of this EZ remains in the Earth. And so this is one possibility to explain the vast negative charge of the Earth. It could lie in the water. So another hypothesis. And now, if so, we look at the clouds and ask the question, what keeps the clouds suspended? So the Earth has all of this negative charge, possibly from easy water, and the clouds, so what's a cloud made up of? Cloud is made up of these little droplets of water which have negative charge because of an easy envelope around each one. And since they have negative charge, you'd expect that they would repel each other, but in fact, they must attract each other because they come together as clouds. And how do they do it? Well, once again, it was Feynman who came up with the idea, and without violating any fundamental laws of physics, that he said, like likes like. So these are like charges. They like each other, so they come together because of an intermediate of unlikes. So it's the positive charges in the atmosphere that gather in between the negative charges to make them come together. But the cloud still retains a net negative charge. And if it does, then the clouds may keep up simply by a repulsive force between the net negative charge of the cloud and the net negative charge of the Earth. And so if you have a higher cloud, the higher cloud may be higher simply because it has more negative charge and the repulsive force is stronger, so it stays up, and this one obviously would have less negative charge. And if you think about this hypothesis, then it becomes easy to explain why sometimes you see layers of clouds. And these layers have been difficult to explain in terms of the usual temperature and pressure. And so you can imagine that the cloud up here has a lot of negative charge. This one has a medium amount, and this one has a lower negative charge, and you can explain it. So in terms of cloud suspension, a possibility is that the reason the clouds are up there is simply by repulsion from the Earth. Now, and this provides a hint about the main topic of what I want to talk about, which is the birds. What keeps the birds up? And the question will be, well, is it a similar kind of mechanism that is? So let me add one more point in terms of repulsion. Volcanoes. This is a famous volcanic peak in California, an iconic one. This one is dormant at the moment, but others are more active, like this one in Chile. And you notice it's hard to see the volcanic peak here, but this part should be familiar, and the dust that is up in the air and stays up there, and this one illuminated by the sun. Well, the most famous one, I think, was Krakatoa, which blew in 1883. And there were no photographs of it because if you were close enough to photograph it, you were dead. It was a really powerful volcano. This is what's left right now of Krakatoa. And it exists in Indonesia, right around here. And here's an interesting map, because this used to be Krakatoa before the eruption. Now, this is Krakatoa, and that volcanic photo that I showed you of the remnant. So this entire island blew away, and the entire island blew into the sky. And because of these particles, one of the aftermaths was suspended dust up there, which blocked the sunlight and which gave rise to a summer without warmth, a wintry kind of summer, which is sort of illustrated here. But not only that, but it gave rise to beautiful red sunsets for 2 years. So the particles were up there refracting the light, and up there for 2 years. So 2 years is really what I want to stress. And the question that you might ask, or maybe you haven't, is how is it possible that particles could stay up for 2 years? No, they're up there. They're pulled by gravity. They're heavier than air. They should come down. Is it really? I mean, the evidence is that the particles stay up there, but 2 years? It takes quite a long time. And so the question I raise is, could negative charge create the loft? Is it possible that the volcanic eruption is charged in some way? Well, it's clearly charged because you can see in many of the eruptions, you can see lightning occurring during the eruption. So it's possible that the dust that's up there remains up there for a long period of time because of repulsion from the Earth. It's the same with dust particles in your office or your bedroom, they're floating in the air. So these are heavier than air. They're pulled by gravitation. How is it possible that they stay up? Same argument. In fact, here's something, if you're particularly fastidious about keeping clean, you'll know that if you look carefully up on the ceiling, remember, dust is heavier than air. The particles will stick to the ceiling. And same question, could the negatively charged dust induce opposite charge next to it and thereby stick indefinitely to the top? And the same thing with dust storms, otherwise called haboob. They can go hundreds of meters high, and the question is, well, what keeps them up? We have something that should be pulled by gravitation. And if you happen to live in Phoenix or a region like that, you can see these dust storms coming in. And the question is, again, is it possible that charge repulsion is responsible for keeping this up? And if not that, what is it? And so a question that arises, I've been mentioning negative charge at the time. How could any object acquire negative charge? Well, I found out actually fairly recently myself about the so-called triboelectric effect, and that is, if you have material 1 sliding past material 2 because the surfaces are rough, they rub on one another. Inevitably, one becomes positive, one becomes negative. And there are lots of physicists who are studying this, and it's pretty common to know if you take rabbit's fur and rub it on Teflon, they both become charged. And the same thing with silk on glass. So you rub two things together, one becomes negative, one becomes positive. It's natural. And this is a list which you might or might not be able to see from where you're sitting, listing common substances. And some of them have a tendency to become more positive, and some have a tendency to become more negative. And they're listed here. So, for example, if you rub this one, I have trouble seeing myself, but like rabbit's fur on gold, you'll find that the rabbit's fur becomes positive and the gold becomes negative because gold is lower on here. So one of the most interesting findings, I almost fell out of my seat when I saw it, is that the highest one of all is air. So what does that mean? Well, it means that if you blow air on anything, the air becomes positive and that thing becomes negative. This is really important. So, for example, you use the hairdryer and your hair becomes fluffy. Fluffy, it means that the hairs are repelling each other. Well, what's going on there? Well, what happens is that the hair becomes negatively charged, if you look at the triboelectric series, and the air becomes positively charged. And so the hairs repel each other and become fluffy for at least 30 minutes, and you look beautiful. Or some of us do. Some of us, it's impossible. Okay, and so now here's another common thing is the Frisbee. I don't know about you, but the first time I threw a Frisbee, I was astonished at how long the Frisbee could stay up. You expect you throw a rock and it goes down, but the Frisbee, as long as it keeps rotating, it stays up. And so what's going on here? And, well, the edge of the Frisbee is rubbing against the air. So the Frisbee, according to the triboelectric series, must acquire a negative charge. And of course, the negative charge will repel from the Earth. So as long as the Frisbee is turning, the Frisbee should stay up. But when it stops turning, it plops down. Now, the usual explanation is for the reason why it stays up is the iconic shape of the edge of the Frisbee. And through various aerodynamic arguments, it stays up. But that's a little bit difficult to believe because Frisbees are vastly different shape, like this shape right here. Without that iconic edge, they fly just as well. And of course, they're also rotating through the air, so the same principle should apply. It's got negative charge. The Earth is negative, and the question is, does it stay up because of the negative charge? Here's a slide I just got. It comes from Scientific American. It was taken in Iraq. We're constantly at war in the Middle East, and so we have these military airplanes, and there's a helicopter, and the helicopter rotor blades are turning around. And in this particular case, because of the heavy dust and high conductivity, it's apparently discharging into the air. And, we're talking thousands of volts for something like this to happen. So, and people dealing with helicopters are advised to make sure that the helicopter is grounded before you touch it. Otherwise, death can ensue. So that's another example. And, of course, the question that arises is this charge, at least in part, responsible for keeping the helicopter up? So here's another example. Now, here's a paper plane, and if you're good at this sort of thing, you can fly the paper plane for long distances. And if you notice the shape of the wings, there's no shape. It's flat. So those of you who are familiar with Bernoullis Principle, I'll show that in a moment, there's no possibility for that to work because the wings are flat, yet it flies perfectly well, you see. And so the question is, as the paper is moving through the air, the paper should acquire a negative charge according to the triboelectric effect. And is it possible that it's the negative charge on the paper that keeps it aloft? And the same principle for glider planes. Now, these can travel up to 2,000 kilometers without crashing. and of course, the plane is going through the air. The wings should acquire a negative charge. And the question is, could negative charges keep not just the glider plane, but all of the objects that I'm talking about? They all stay aloft. Is it possible that the reason they stay aloft has something to do with the charges that they acquire? And that leads to the question. The main question is, could negative charge keep the birds aloft? Well, actually, there have been measurements of the electrical potential of flocks of birds. They report thousands of volts. It may surprise you, but this has been reported. And obviously, they had no idea what's going on, but the measurements are made. So the question that could be in your mind if you're not falling asleep from that gargantuan lunch is, well, we all know about charge forces. They're trivially weak, right? They can hardly do anything. How is it possible that charge forces could keep all of these heavy objects suspended? It's probably what you're thinking. I want to show you that that viewpoint is completely wrong. I illustrate with a couple of slides. So one of them is here. These are two old-fashioned light bulbs, 120 watts to make the arithmetic simple in both of them. And suppose, this is a thought experiment, suppose you could collect, the electrons are running through here to give light and heat, and suppose you could collect 1 second's worth of these electrons that flow through the filament, compress them to a point, this is a thought experiment, and put them all down here on the ground, and do the same thing 1 meter apart, do the same thing from another light bulb, so you have 1 second's worth of charge here and 1 second here. Now, obviously they repel each other, and since this one can't go down, this one wants to go up. And the question is, how much weight would you have to put on top of this cluster in order to prevent the upward movement? And of course, you have no idea of what the answer is, but the answer is, I first calculated in terms of jumbo jets, and the answer in terms of jumbo jets is 5,000 jumbo jets, but my son, who's the artist, couldn't draw a stack of jumbo jets, so equivalent to about 50,000 garbage trucks stacked. That's the amount of weight that you'd need to put on to prevent the upward movement of that little cluster of charges. Another example, which is maybe more vivid, is something like this. I've shown it before. Some of you may remember. So you take a guy and his girlfriend, and you suspend her somehow up here. The method of suspension is not so important. You can imagine a little net or something underneath, or some springs holding her. They would like to come together, of course, but you're doing something that prevents them from coming together. So you remove 1% of the electrons from the guy and 1% of the electrons from the woman. And so by removing 1% of the electrons, This guy has a net positive charge, and the woman has a net positive charge, so they repel each other. So the same story now is, how much weight would you have to put on her to prevent her levitation? Any idea? Pardon? No, I didn't. Yeah, well, okay, son. Yeah, I've asked various people, and I get numbers like 10 kilograms, and some say, well, the amount of weight that it's her weight that you'd have to put on her back to prevent her. Well, the answer was calculated, again, by none other than the famous Nobel laureate Richard Feynman, and he said the amount of weight that you have to put on her is equal to the weight of the Earth. So, main point, this is his calculation, not mine. Main point is that you think of charge forces as being trivial, small. They're huge, absolutely huge. And those are just two of many examples. So charge forces can be enormous. And and birds moving through the air must get charged because, this bird is flapping its wings, and the wing is moving through the air, and therefore the bird must get negatively charged from the triboelectric effect, must repel the Earth. And I've just demonstrated to you that the force, the magnitude of the forces from this kind of effect can be just huge, much, much larger than you would imagine. And the same thing applies to birds that are soaring in the air. They don't flap their wings, but they're moving their wing through the air. They also get charged in much the same way. So I raised the question, is it possible that birds are able to levitate by repulsion from the Earth? So I'm not sure if you buy this hypothesis as a reasonable alternative to the current view, which I'll go into in a moment, or not. But one question you might raise is, well, okay, maybe the birds can stay up, but how do they go forward? What causes forward thrust? Now, here comes something from physics and electrical engineering, and something that I learned in my younger days. And if you have a capacitor, which is shown here, plus, minus, it generates an electric field this way. And if you have a dielectric rod moving through here, it turns out it's a known principle of electrostatics that the rod gets sucked into the capacitor. And then let me explain. This capacitor, you see, this positive charge induces a negative charge here, but this negative charge induces a positive charge here. So the two of them balance out, and effectively, this contributes nothing to anything, right? But if you look at the one at the tip, the reason the rod gets sucked in to the electric field, that's the important thing, is that the rest of the capacitor beyond here, you see, this positive charge is attracted to this negative charge, and this positive charge here, negative charge, is attracted to this positive charge. So you get a component of the electric field that bends, as you see here, and you get a net force which wants to pull this charge nearer to this charge, and this one nearer to this one, so the dielectric rod gets sucked into the electric field. Now, in another case, where this rod is now negatively charged, which is more relevant to the situation, you still get the same kind of force here. But now this capacitor contributes more because this positive charge attracts this negative, but you've also got more negative here. So you get a big upward force and a smaller downward force of this positive attracting this negative. So that means that you get both levitation, as I mentioned before, repulsion from the Earth, which would be sitting down here, but also forward thrust. So you actually, the bird then, if this represents the bird, a negatively charged bird, the bird stays up and it moves forward by the same mechanism. You get two for the price of one. Now, some of you are thinking, well, gee, I learned that the reason these things stay up is because of Bernoullis principle. So what's Bernoullis principle? Here's a good estimate. So here's an airfoil, like a wing. It could be the wing of a plane or the wing of a bird. And you remember, the upper surface is curved this way, and the lower surface is flat. And so Bernoullis' principle says, well, if you got air coming this way, the path length here is longer than the path length here, assuming they arrive at the same time here. And because this one is moving faster, you have high speed, therefore reduced pressure. Not so easy to understand, but this is the principle. And because of the reduced pressure here compared to here, you get lift. Well, Professor Holger Bobinski at Cambridge University in the aeronautics department tested the principle. And remember, the underlying principle is that the air needs to go from the front and reach the back at the same time, whether it's going this way or this way. And you might think, why should it? He tested that using models like this with smoke. And he determined that the flow above the wing and the flow below the wing don't reach the back of the wing at the same time. So a critical condition underlying Bernoullis' principle, according to him, is violated. Also, there's this. You know, if Bernoullis' principle is keeping this plane up, then I guess it's simple logic to think that Bernoullis' principle ought to crash the plane. And, you know, some people think that these maneuvers occur only very briefly where the plane goes up and down, but it's not true. So here's an example, you know, of long-range, upside-down flying. And I know a test pilot, a stunt pilot, who tells me she does this all the time, and this is long-term. There's also a video of some Austrian guy who uses, there are two biplanes doing this, and he's actually climbing from one to the other during their flight. It's amazing to watch. But anyway, these planes can fly upside down for extended periods of time. I think many of you know this, but we don't think about it. But what I didn't know until a very short time ago is that the same thing, upside down flying, could be done by birds. So there's a paper in Nature, it's an old paper, 1931, ravens flying upside down. So, you know, you don't see this too often. However, another report in Nature a year or two later, who was watching birds in Iceland, he said there are flocks of birds who do this thing all the time. And they can fly up to 1,000 meters upside down. So what happened to Bernoulli? How do they manage to do this? And then another violation is what you might call modern wing shapes. I don't know if you've ever done it, but if you walk out on the tarmac and look at the shape of the wing for the smaller planes, they look kind of flat on top. And in fact, these wings, these are wings that appeared in the 1960s, right? And these are they're called, I think, critical shape or something like this. But here are some of the patterns of wing shape that came out and were used in many planes. So again, there's something wrong with Bernoullis' principle, and I guess it's summarized here by this book that appeared in 1997. Stop abusing Bernoulli, how airplanes really fly. So I showed you these slides to say that most of us think that it's Bernoullis' principle that keeps everything up. These slides imply that there's something wrong with Bernoullis' principle, that is not the mechanism that we're talking about. Well, I started to get interested myself in flying when, you know, Seattle has a lot of water, and there's a ferry that goes from Seattle to a nearby Bainbridge Island. And I'm watching to see what goes on, and I'm looking out on the side, and this is a kid feeding popcorn, and here are the seagulls. And I'm watching the seagulls, and I see that the seagulls have got their wings out, hardly ever flapping, and going alongside the ferry, sometimes in front, sometimes in back, sometimes even far out, like this. The ferry is going at maybe 30 kilometers per hour, and there might be a headwind of another 20 kilometers per hour. So the bird is flying 50 kilometers per hour, just like this. Very happy. They look content, and they're having a good time doing it. How do they do it is a question that I thought about. And so one guy says, well, obviously, there are vertical winds that are keeping the seagulls up. And that's certainly a possibility. But if you think about the argument, if you have updraft going this way, you must have downdraft other places, because if you have only updrafts, the air is lifting up and we can't breathe anymore. You see, so that's impossible. You can have updraft, but also downdrafts. And you'd expect that if the bird got caught in one of the downdrafts, there would be a problem. Well, I actually tried to measure this myself with my hand. And outside on the deck of my home, sometimes you could see the birds flying, and sometimes flocks of birds are flying without any flapping. And so I asked myself, if the air is moving upward, I ought to be able to detect it. Put my hand out, tried hard to feel some flow. You can do this yourself. I couldn't feel anything. And then I took a balloon. My daughter had a birthday party the night before, and I took the balloon, and I thought, if the air is moving upward, surely the balloon would move upward, down. So demonstrably, the birds were flying without flapping their wings. I could detect no updraft at all. Another point about updrafts, I was in Africa a long time ago on a safari, and was looking at there were hawks we were looking at that were flying. They would take off sometime in the middle of the day, and no wing flapping, essentially zero, maybe to get started, but beyond that they'd be coming and circling and thinking about, well, it could be an updraft, but if you think about it, if there's an updraft here, you need something to replace the air that's missing, and therefore you ought to be able to feel some kind of wind. We could feel no wind, and this happened several times, various conferences and such. You could see the birds, sometimes seagulls, gliding, couldn't feel any breeze whatsoever. Well, a person who has been studying this sort of thing, electricity in flight, actually more recently, Ulrich Warnke, has been studying the bees who get lost because of electromagnetic waves. But he also studied the electricity in flight. And here's one experiment that he did, which I think is telling. So he put a sensor, sensor that measures electric field at this position. He was studying bees. And this is the distance here, the proximity to this. And he put the meter here, and the bee would be approaching. And as the bee was approaching, the first thing is that the electric field increased. And this is what you might expect if the bee contains some charge. But even more interesting, there was a frequency that occurred, and 5 milliseconds in between, and that was exactly the wing beat frequency, 5 milliseconds between wing beats. So it looks not only that the bee is charged, but that the wings, the flapping of the wings, have something to do with the magnitude of the electric charge that was measured. And so many people have actually measured, at least I've seen at least a half dozen, have measured the charge on birds. So you can take an electrometer and do that. Now, if you stick the electrometer, if you happen to stick it around here, where the positive charges would gather around the negative ones, you might expect to find a positive electrical potential. If you stick it in the bird, who doesn't like it too much, then you might expect a negative, but of course of much lower magnitude than because the charges are spread all around the bird. So people have made measurements, and they're all over the place. Some report negative, some report positive, and the magnitudes are vastly different. But everybody reports charge. There's no question about the charge. So a related question is, birds have feathers, right? And a question that you might ask is regarding the mechanism is, well, why do birds have feathers? And, one idea is that, at first, this is a famous quote from an ornithologist. All birds have feathers, and all creatures with feathers are birds. So feathers are unique to birds. So why on earth do birds have feathers? One popular response to this is it makes them lighter. But if you think about it, a bird, if you have two equal birds and you add feathers, it's not going to get lighter, it gets heavier. So I think that argument is fallacious. Another idea is that the birds need to keep warm. That can make a lot of sense in the Arctic, but in the tropics, it doesn't. You can imagine that there's no particular need for the birds to keep warm. I think another possible explanation is embedded in the structure of feathers. If you look at the microstructure, it looks something like this. So these are keratin fibers, and you see it's like a matrix, and the matrix has a lot of openings and a lot of surfaces. So if you could imagine that the feather is moving in the air, the opportunity for this to gather negative charge is huge because the air is moving right past it. And so this is now questions about migration. That birds migrate, and sometimes these birds can migrate over thousands of miles without stopping for a hamburger. And so that's one issue. The second issue is where do they, how do they sleep? Excuse me. Experimental studies have shown that just like us, the birds need to sleep. So you can think about what's going on, and it appears that like on a 5-day migration, for 5 days without sleeping, we'd go nuts, even more than I am right now. But the birds need to do the same thing. But if they're migrating for 5 days, they must be sleeping during the migration. Otherwise, they shouldn't be able to remain as sane as we presume they are. And so we imagine a situation like this. Now, so one of the anomalies of migration is that the birds, if they're crossing a mountain range, if you were crossing a mountain range, you'd go through the valleys. Well, sometimes the birds do that, but other times the birds will actually climb above the highest mountain peaks. Birds have been detected over Mount Everest. Now, you'd think that this is really bird brain activity because this is not a very hospitable environment we're talking about. The partial pressure of oxygen is like 20% of what it is down here. What does the bird do? Opportunities for food are nil, let alone the freezing temperatures. So how is it possible that a bird will choose to go over Mount Everest instead of in the valleys? Well, if the bird is sleeping, it effectively is acting as a projectile. If it acts like a projectile, you may think about what happens when you have a mountain. When you have, if you have negative charge down here, and you have a peak sticking up, the negative charge will gather right at the peak, and it will attract more positive charge from the environment. And so the electric field here will be very high compared to other places. And remember the principle that we talked about, that the negatively charged rod will be drawn into the electric field of a capacitor. So basically we have a capacitor here with plus and minus. And so if you've got a bird that's sitting here, which is negatively charged, it's going to be drawn into the electric field, just as the rod is drawn into the electric field. So this is a possible mechanism to account for the bird brain activity of birds flying over Mount Everest instead of inside the valleys. Now, there's another paradox, or anomaly, which is so interesting: energy. So where does the bird get its energy? Well, here's an example. This is the bar-tailed godwit, and it flies first from New Zealand to Alaska, but on the return from Alaska to New Zealand, 8 days non-stop. 8 days flying without any stopping for food, and so this is so interesting. And many scientists are wondering, how is it possible to do this without any food? Because the only possible food, it comes from from the mass of the bird, right? And so the bird should lose weight, just like if you went running for 20 miles, in the process of doing it, you'd lose a few pounds. So one group decided to do a study of this. This is, again, a paper in Nature. If it's in Nature, we must believe it's true. So they studied bird energetics, and they studied songbirds, which look like this, and they go from Panama to Canada, 700 kilometers nonstop. So it should be easy to figure out how much weight you need to lose, because essentially it comes from body fat and such energy. And they did computation, and I don't remember the number, but the weight loss was so much less than expected. It wasn't even close. I can't remember the number, but I think the weight loss was something like 10% of what they expected. So they concluded from that the energy for flying has got to come from somewhere else. It's not coming from the energy that's stored within the bird, that it's mainly external to the bird. And so if you think of a source of energy that's external to the bird, I tend to think of the sun, right? And I think of the sun basically hitting the water and separating charge, which is what we found in the past decade or so, buildup of easy water, negative, and separation of positive charge. And so a question is, could the bird's energy come, so you might say indirectly, from the sun rather than from the bird? And so those of you who are unfamiliar, we have the easy water, which has negative charge next to some surface. If you add more infrared energy, it builds, and it can build substantially. So light, particularly infrared, builds negative charge. And so you have a situation here that you got the negative charge, and light builds the negative charge, which repels the bird, right? And so the energy for flying then ultimately comes from the energy from light, from the sun. So we have a situation here where these are many slides that I've shown you, and in all of these cases, something is staying aloft. And we have myriad reasons that are given for why they stay aloft. This one is staying aloft because of updrafts. This one has something to do with temperature and pressure. This one has to do with the iconic shape of the Frisbee, et cetera, et cetera. So I asked the question, and I pose this just as a hypothesis: is it possible that repulsion from the Earth can explain all of these? Thank you.